So for those of you that have just joined, welcome. Welcome to Electrosonic's Power of Sound 2, designing acoustic-friendly workspaces for better sensory experiences. Thank you for taking the time today to join us and listen to our webinar. So this webinar is intended to serve as a guide by providing a concise discussion of sound, methods for its control, and how to apply acoustic principles to transform auditory comfort and their effect on creative design. So as you know, acoustics is a huge and complicated subject, but we hope by the end of this session, you will have a better understanding of the acoustic design solutions that help create positive working environments, the factors influencing soundscape quality and the impact on design decisions, and how to apply these acoustical principles to transform listening comfort within the workplace. So just a few housekeeping bits and pieces before we get going. So today's webinar will run for approximately 40 minutes, including Q&A. It is being recorded and you will be sent a copy of the recording and the slides after the webinar. So we do welcome questions, so please feel free to put them in the Q&A box and we will do our best to answer as many as we can at the end. And then if you think of a question following the webinar, then please feel free to email us at the email address on the screen here. So now I'd like to introduce you to your Electrosonic host for the webinar. My name is Gemma and I'm the Marketing Manager at Electrosonic. I have two great speakers for you today, both who have extensive experience within the AV industry and acoustics. So Jim is our Head of Solutions. He has 30 years experience in the industry. He has worked in live events, specialist AV consultancy, and for major technology manufacturers. Nerjus has been designing and implementing bespoke audiovisual solutions for the last 14 years, and he's always had an interest in audio and music from a very young age. He did his master's in electronics, where he dedicated his thesis to acoustical measurement. So, although acoustics is a relatively new science, it was recognised and used centuries ago. At the theatre at Epidurus in Greece, the shape and distance between the steps allows an audience of 14,000 to clearly hear the actors and musicians without the need for audio amplification, which even in today's standards would be quite a feat. So made of limestone, it is the shape and distance between the steps that act as a low frequency filter, which absorbs unwanted audience hum and wind noise, which allows the speech to go from the stage to reach the furthest edges of the theatre. Nowadays, advancements in acoustical science allows us to apply these principles to ensure workplaces provide comfortable environments while increasing employee productivity and efficiency. So why do acoustics in the workplace even matter? So the sonic environment, it can have a profound effect on a human body, mind and body. Noise can affect our concentration levels, productivity, memory, energy levels, and even our health. Sound is usually only often considered for specialty projects like concert halls and auditoriums. However, most other projects could benefit from intentional acoustic attention to get the best out of any given environment. So here you can see a typical modern day workplace. It has open plan offices, huddle spaces, meeting room, lobby areas, co-working spaces. So while these environments have been tastefully designed for aesthetics, sound has not always been considered. So design that includes glass, rugged exposed brick walling, stunning hardwood and concrete floors, they all reflect sound and can create echoes while compounding environmental noises. Every workspace will be affected by different sounds. A lobby may experience external noise from a nearby busy road. An open plan office has to contend with people chatting, photocopiers churning, the hum of heating and cooling units, the relentless typing on keyboards and phones ringing. Meeting rooms are usually placed nearby to the open plan environment and will be affected by the noise generated from these adjacent spaces. So architects, contractors and building professionals can create better workplace environments by considering the acoustics of a workplace during the design phase. Sound control has the extraordinary ability to convert just about any space into a more comfortable, creative and productive environment. So we today are going to look at the 10 factors influencing soundscape quality in a modern day workplace. So these will serve as a starting point for you to think about what acoustic design decisions you might need to make in an enterprise workplace project. So before we dive into each of these, I'm going to pass you across to Nerjus, who will explain what sound is.
Hi Gemma, and hello everyone. Before we dive deeper into the details that affect space oral experiences, let's talk about what sound actually is. Sound is produced by object vibrations, which excite surrounding air molecules. It travels in all directions from the source as a pressure wave in the air, much the same way as waves travel through the water in a pond when pebble is dropped into it. Sound waves travel through the air as alternating regions of compressed and rarefied air. Two physical characteristics apply to sound, as they are pitch or frequency and loudness or amplitude. Frequency is a number of times per second that sound pressure alternates above and below atmospheric pressure. Frequency is measured in cycles per second and is expressed in units of hertz. A frequency of 1000 Hz means sound pressure alternated 1000 times per second. Amplitude defines the pressure difference between compressed and rarefied air. The higher the sound amplitude, the higher the air pressure. Sound becomes increasingly interesting when we look into how it transmits or interacts with a medium, in our case air and any other surface within the space. In most cases, sound or noise is transmitted both as airborne and structure-borne sound. For example, speech is an airborne sound until it strikes a structure, like a wall, and becomes structure-borne. Then, by internal wall vibrations, it is radiated out on the other side as airborne to the listener in a particular adjacent room or area. Sound can be direct or reflected. Direct sound travels in direct path from source to receiver. This path is always the shortest and does not strike any surfaces while traveling. Direct sound diminishes in intensity as the distance between source and receiver is increased. The reflected sound strikes a single or multiple surfaces before reaching the receiver. When a sound wave strikes a surface, its direction changes in the same fashion as a ball bouncing off a wall. What we hear within the space is always the sum of direct and reflected sounds. Here you can see the simulation of how sound transmits in an enclosed space. You can clearly see how sound acts like a wave while filling the space. Sound reflects from walls or boundaries back into the space. This simulation only shows first 50 milliseconds of sound propagation. It is this initial instance of sound propagation that defines the acoustical properties of space or soundscape sonics. So what impacts the sound quality? Space soundscape is defined by its boundaries. In other words, materials that are being used for walls, floors, ceiling, and anything in between. Acoustical waves interacts with these surfaces where they can be transmitted through, reflected, diffused, or absorbed. Here is a quick definition of each. Transmission. This is when sound penetrates through and continues past the surface. Specular reflection. This is when sound reflects off smooth and hard surfaces at the same angle from which it came. Diffused reflection. Here sound reflection is scattered by faceted rough or generally irregular surfaces. Absorption. This is when sound energy is trapped in soft, porous surfaces. Every material carries a combination of these properties. Some are more effective at absorbing sound energy, while others are better at reflecting or diffusing it. Soundscape sonics are also affected by the shape of the environment. For example, wall heights, distance, and the angles between the walls can have a big impact on how soundscape sounds. In order to evaluate the soundscape, we take a holistic source path receiver view. Sound can be controlled at the source, along its path, and at the receiver. The biggest contributor to the soundscape quality is the path, or everything that is in between the source and the receiver. One of the most important factors affecting soundscape quality is reverberation time. Sound in room will repeatedly bounce off surfaces such as floor, walls, ceiling, windows, or tables. The reverberation time is a measure of time required for the sound to fade away in an enclosed area after the source of sound has stopped. The red arrows in the diagram indicate direction of sound wave and its reflections. The reflections that hit the floor and the ceiling before reaching the receiver are called first-order reflections. The reflections that bounce off surface twice are called second-order reflections. Sound loses energy by absorption at each reflection, where its level is reduced. When we work on optimizing room acoustical performance, we work with first, second, and third-order reflections. When the sound finally reaches the receiver, it is made up of both direct and reflected sounds. While there are substantial variation within programs, some spaces like recording studios require less reverberation than others, for example, concert halls. By adhering to recommended reverberation times, it can help make space feel the way it was designed to feel. Reverberation is fundamental to experiential architecture, both on conscious and unconscious level. As you can see from the RT60 chart, different spaces have different suggested reverberation times to achieve speech intelligibility and acoustical comfort. For example, open office space will have a different reverberation time to an auditorium. What is RT60? The reverberation time of RT60 is defined as the time required for sound energy to decay in the space by 60 decibels. For example, if sound in a room took 3 seconds to decay from 100 decibels to 40 decibels, RT60 time would be 3 seconds. If we can't achieve the desired RT60 times, then we need to apply additional acoustical treatments. As you can see in the right-hand diagram, a suspended ceiling and acoustical wall absorbers have been installed within the space. This treatment helps to reduce first, second, and third order reflections. You can see in the diagram, the fainter colored red arrows show sound energy being absorbed. This reduced amount of reflected sound makes speech clearer. Acoustical treatment is a fine art. Too much of the treatment or applying treatment to the wrong surfaces can result in negative outcomes. We can use reflectograms to carry out our detailed analysis of what acoustical treatment is required. The reflectogram is the representation of what is being received or heard in a particular location of the space. The first red vertical line of the left of the graph indicates direct sound from the source signal. The green lines are the first, second, and third order reflections from within the space. Every line height represents sound energy. The distance from the red line to the green lines specify the delay when the reflections occur. By knowing the speed of sound and the delay, we can identify surfaces which need to be treated. The next factor that we will discuss is sound absorption and how this directly affects the reverberations. Acoustic absorption refers to a process by which a material, structure, or object takes in sound energy and transforms it into another form of energy, that is internal vibrations or heat. The energy transformed into heat is said to have been lost. The efficiency of this process is quantified by sound absorption coefficient or noise reduction coefficient. All materials absorb sound energy to some degree. Every material has a different sound absorption level or noise reduction capability. These depend on material's density, porosity, tensile strength, and surface finish. NRC or noise reduction coefficient ratings are frequently expressed in product literature and specifications by a single number. The higher a material's NRC rating, the more effective it is at absorbing sound. As you can see here on its chart, fiberglass is a good sound absorber. Choosing and applying absorptive materials is a fine art. It is not only what materials are used, it is how they are used contribute to the space soundscape quality. The images on the screen demonstrate the strategies that can help make this absorption more effective and improve sound quality. It is recommended to place absorptive materials on the surfaces closest to the sound source, that is people. As you can see from the diagram on the left, narrow spaces, this might be the vertical surfaces, and in wide spaces, this might be the horizontal surfaces. As you can see from the diagram on the right, you can also offset absorptive materials to increase the sound absorbing surface area. This principle does not only allow to double the absorbing surface area, but also trap reverberating sound. Two other methods using absorptive materials to increase soundscape quality include having a direct line of sight between sound source and absorptive material. It is sad to be said that absorptive materials can be placed behind other surfaces in order to reduce sound spill between different floors or rooms. We will also need to distribute absorptive materials evenly to achieve consistent improvements to space acoustics. However, there could be exceptions where clustering could be beneficial, like in workplace coffee areas. The relationship between acoustical treatment and sound absorption is not linear. Before sound absorption is noticeable, you must add a particular amount of absorptive material. Adding more treatment does not always equal to better results. There is a saturation point where adding more absorptive material has little to no effect. Each area will require a specific amount of acoustical treatment to bring the best results.
Thank you, Nerjus. And before we start, folks, just a quick apology. As I'm sure you can appreciate, we're doing this remotely today, and the chap across the road in the woods has decided today is a good day to bring out the industrial mower and the chainsaw. So there's a little bit of background occasionally. Apologies, can't do anything about that one. So now we'll discuss some of the factors which influence the sound space quality, starting with the sound reduction index. This is used to measure the level of sound insulation provided by a structure, such as a wall, window, door, or ventilation path. This parameter gives a value to the sound privacy between these rooms. In other words, this is the level of sound insulation provided. It's the difference between the sound intensity that hits one side of an object, such as the wall, door, window, or, as you can see in this image, a partition, and the sound intensity measured on the other side, expressed in decibels. There are many different wall construction techniques available to enable isolation between rooms, and different construction techniques affect how sound travels between spaces. Simple things such as adding air gaps or additional layers of plasterboard can make a huge difference. Referring to a material's NRC rating can assist with specifying the appropriate material. So when you're designing a space, it's a good idea to group noisy areas together and the quiet areas together with appropriate distance or materials between them. You should identify the major noise sources, including people, equipment, kitchens, and communal areas, and locate them as far from critical quiet areas as possible. As the level of sound rises in an open plan office due to surrounding conversations or air conditioning hum, for example, the speakers tend to raise their own voices, increasing the noise floor, the background noise, of the space. In this way, noise can compound noise, creating a sonic environment that's not conducive to working. Most building surfaces, including heating, ventilation, and air conditioning systems, as well as electrical power generators, involve rotation, reciprocation, or otherwise vibrating equipment. When such sources are located near critical occupied spaces and are directly attached to the supporting structure, serious problems can arise from both airborne and direct structure-borne sound transmission. The complete treatment of mechanical electrical equipment noise is critical to the success of the overall building space. This type of structure-borne sound can be controlled at the source by resilient mounting of equipment using special decoupling or isolation constructions. Isolation describes a process of reducing or attenuating noise or vibration. Here you can see different materials, specifically fiberglass and gypsum board, provide different levels of absorption and isolation for mechanical equipment. The example mechanical device generates about 70 dB in an open space. That's about the same volume as a vacuum cleaner. You can see on the slide how running combinations of fiberglass bats and gypsum board absorb and reflect the sound differently and result in different levels of sound after treatment. The best result here of 43 dB is about the sound level in a quiet library. Attenuators or duct silencers are usually mounted in air conditioning systems adjacent to fans and include fiber and air pockets to absorb noise. One of the key elements for quiet HVAC design is to use larger and wider ducts so that the air can move slower yet still supply the correct volume or quantity of air. It's good to note that smaller air conditioning units often utilize fast-moving air currents, which can easily become noisy. So there are published guidelines for the NR ratings for specific spaces. The noise rating levels and curves provide a set of targets for mechanical or background noise levels present in different spaces before any AV is added. The UK Building Regulations 2010 approved document E sets these out as official guidance. The diagram on the left here shows a green line, which records the measured room noise in a completed space. It reveals some humps between the ranges of NR50 and NR60 at specific frequencies. This information allows us to analyze what the problematic frequencies are and thus select appropriate acoustic materials to address these problem areas. Doing this properly, we should be able to absorb these lumps in mid and mid-high frequencies and work to attain a rating of NR50 for this space. The diagram on the left has been extrapolated into the table, which makes it a little easier to read and compare. A sound masking system raises the background sound levels in an office environment in order to mask speech sound. You can see on the images above that the background chatter, in red, is regularly much higher in volume than the background noise, in green, and so could be considered quite intrusive. But looking to the right-hand image, the addition of sound masking effectively raises the ambient noise level to mask this background conversation. You will naturally tune out the ambient noise, so your conversation appears clearer. Sound masking systems use a mix of different sounds to appear more natural. As you can see here, white noise is only one noise color. It's the one which most people have heard of, but there are several noise colors. Sound masking systems are often limited to frequencies of human speech, but can also use more biophilic natural sounds like babbling water, for example here the green noise. When introducing sound masking to an environment, consider slowly phasing it in a few decibels each day so that the users of the area gradually accept this as the normal background level. The Speech Transmission Index is a measure of speech transmission quality or speech clarity. This parameter is affected by how materials in a space are arranged and combined together. It's also affected by the other existing audio sources in the space, such as background noise, air conditioning, passing traffic examples. An STI of 0.5 is considered a desirable minimum rating for most applications. Of course, All interior room finishes either diffuse or absorb sound, for example, soft furniture, carpets, and heavy fabrics. Sound absorptive materials are used not only to reduce reverberant sound in a space, but also to enhance speech intelligibility. Adequate sound diffusion is particularly important in auditoriums and concert halls because it promotes a uniform distribution of sound. Diffusion is the scattering of sound energy by a complex surface. In these spaces, this accentuates the natural qualities of speech and music and prevents the rise of acoustical defects within the room, such as echoes. Absorptive materials can be added onto, within, or placed between surfaces to absorb sound. Here we show some examples of each. As you can see, different materials look better in each situation, and of course they all have different price points. A successful treatment program might involve several materials or techniques. However, it's far better to try and plan this beforehand than try to fix a room after construction. But there are some architectural do's and don'ts to follow in order to maximize sound quality. For example, the orientation of walls and surfaces. There are some rules of thumb to keep in mind when working with reflective surfaces like gypsum board and glass. Don't put reflective surfaces parallel to one another, as this can cause a disturbing flutter echo, which means a series of echoes in rapid succession that really do hinder the clarity of sound. Some parallel walls create standing waves or room nodes, which also affect room acoustics. An example of this could be that awkward box-shaped meeting room. Do orient reflective surfaces perpendicular, so sound cannot bounce between surfaces and flutter echo won't occur. Other options include angling the reflective surfaces so sound will be directed away from the other parallel surface, or add texture to reflective surface so it can absorb some of that energy. Gypsum board and glass both have low NRC ratings, while fabric wrap panels, depending on the thickness, and heavy carpets have a high NRC value, therefore providing better noise reduction. Beyond absorptive ceiling, wall, or floor tiles, there are several other ways to reduce noise in a room. Fabric wrap panels mounted on the walls and ceilings can easily be applied to add absorption into a room. Furniture can be used to disrupt the path of sound energy, and high booths like these shown here can block sound close to a listener's ear. We'll talk more about ceiling baffles in a moment. You can use sculptural elements to both scatter and absorb sound. They can also be used to incorporate lighting. Clouds or hanging panels are particularly useful. As they're suspended, they offer increased surface area for absorption, as both sides are exposed to sound within the room. With all ceiling-mounted treatments, care should be taken to avoid interference with critical building systems, such as fire detection and suppression systems. And of course, screens and movable panels can be used to divide a space, provide privacy and a slight acoustic barrier. Beyond absorptive ceiling, wall, or floor tiles, there are several other ways to reduce noise in a room. Fabric wrap panels mounted on the walls and ceilings can easily be applied to add absorption into a room. Furniture can be used to disrupt the path of sound energy, and high booths like these shown here. Oh, my slider went there, apologies. Here are a few examples of creative acoustical ceiling design. Acoustical baffles contain some absorptive materials. This solution helps to absorb unwanted reflections and reverberations in workspace environments. Baffles diffuse and absorb the sound and help stop sound distribution in open spaces. Here you can see that the most commonly used acoustic solutions in a typical open plan office space include absorptive materials, here in the furniture, screens, or in the ceiling baffles, or sound masking systems. Conference rooms are increasingly used for both teleconferencing and video conferencing, as well as face-to-face meetings, and these functions require careful acoustic design. For example, placing microphones in the ceiling is very convenient, much neater, and allows for flexible furniture to be used. But placing these near HVAC outlets and other high-level services can cause interference and produce a negative meeting experience. For these reasons, it's advisable to bring in an AV design consultant at the early stages of planning to avoid such issues. In a large auditorium or theatre such as this, the seating, wall panels, ceiling contours, and any hanging elements are great opportunities for absorption. Remember that diffusion in a space like this is key also. That said, it's vital to reduce direct reflection from the back wall, which will distract the presenter or performers. So using suitable absorptive materials here is important. These complex spaces benefit from proper design and acoustic modelling. So before you go ahead and spend a lot of time and money, there are acoustical modelling techniques which have been developed to accurately represent the sound fields at an individual seating location in this type of architectural space. This means we can listen, in inverted commas, to the sound performance in the space using a pair of headphones during that design phase before we lay even a single brick. Using these techniques, it's possible to study the effects of architectural design changes on the acoustics so that we can measure, analyse and solve acoustical problems before they even arise. So to recap, in general, the 4 strategies outlined here which can be used to manipulate sound in a space are easily remembered using ABCD. A. We absorb reverberating sound energy to create comfortable room acoustics. B. We will block isolated sounds from transmitting to adjacent spaces. C. We will cover distracting background noise with masking systems or other competing sounds. And we will diffuse, cause for sound energy to spread by radiating it away in many different directions. So, as we reach the conclusion of our webinar, we'd like to remind you that Electrosonic can support you with any of your acoustical design and measurement needs, some of which are detailed on the slide. Please don't hesitate to contact us should you have any questions. We really do look forward to hearing about your amazing projects and your technical challenges.
Thank you, Nerjus, and thank you, Jim. I do hope you found that both interesting and informative. So if you have any questions, then please feel free to put them into the Q&A box. So we'll just give it a couple of minutes. I have got one question that we can start on while we wait for any others to come through. So the question we've got is, what does a drop of 60 dB sound like?
Okay, so that's an interesting question. The 60 dB, it's a relative number, and it is hard to compare that. But I think I could give you an example that could be compared like walking out of the loud pub into the library. That would be the attenuation.
Okay, great. Seeing if we've got any other questions come through. So we haven't got any other questions that, oh, hold on, let me just see. Or someone has stopped hoovering. Yes, that's right, Ella. I have a question. So we've got a question here about acoustical design for disability. Do you have any experience working with design for autism?
Wow, so that's an interesting question, because autism design, that whole inclusivity piece, offers challenges outside of audio as well. We have to consider colours, contrast. So yes, we have worked primarily in some of our public and museum spaces where we've had to have those considerations, but it's quite a large and wide conversation. So if you have something that's more specific, then please contact us after the webinar and we can have a more detailed conversation about that.
Great. Yeah. Okay. So another question we have here are so any thoughts on frequency balance for absorption?
Well, there could be multiple ways of looking into that, but we usually would try to concentrate on a human speech. So we try to drop down a higher frequency, a little bit lower. It all adjusts. It can be, or another way of school of looking into that would be trying to match to the pink noise. So, let more low frequencies in and absorb a little bit of higher frequencies again. Yeah.
Okay, thank you. So just a couple more. What is the standard sound rating of an office v a bedroom?
That's an interesting one. So offices 50 to 60 dB generally is what you'd expect to find from an office space, depending on if it was a private office where you had slab to slab walls and perhaps not too much glass, then you might be able to get that to closer to 45 to 50. But most sort of open plan and general office spaces are going to be closer to NR60. A bedroom, again, you want that sort of library level. You want it to be quiet and peaceful, so low 40s, I guess.
Okay. And just the last one, Sean's asked, are there any studies that point towards health and productivity benefits of good acoustical design?
Yes, we definitely have to, and we could share that with you later in an email.
Yep, lovely. Okay, well, I think we have pretty much come to an end. We just have one more time, just for one more, because it does talk about VC. So Joe's has asked, special considerations for presentation only rooms or rooms with VC.
So rooms with VC, the biggest problem in rooms with VC is generally background noise in the space. The amount of times where you go into VC rooms and what you're hearing at the other end is air conditioning noise, or the general level of noise in the room before anybody starts speaking is so high, and that could be because of traffic or passing people in the corridor, or say air conditioning noise, something like that. That the microphones have to be set at a threshold that they only pick up a louder speaker, and so lower level conversation isn't picked up. So these VC rooms really need thinking about properly. You want these to be very quiet spaces. You want them to have little reflection as possible, and you want them to have properly thought about services and acoustic treatments.
Great. Thank you, Jim. Thank you, Nerjus. So if anyone has any other questions, then please feel free to email us at the address that was shown on the first slide, and say the slides and the recording will be sent to you via email. So thank you very much for taking the time to attend today and listen to what we had to say, and we look forward to seeing you again soon. Thanks very much. Bye-bye.